Okay, so we continue from where we left off in the previous lecture. So one common question is that, all right, that we understand that when P is equal to pi square EI by L square, it is at that Euler's critical load. We understand that we are going to get a buckled shape that is going to be stable. Now, suppose we increase it. Okay, suppose we increase it, then what will happen? Suppose it becomes 1.1, suppose it becomes 1.2 times that. What is going to happen? Now, physically, you forget the maths. Okay, you forget the maths and just think about it. That if you increase from that, so if at P is equal to pi square EI by L square, you have managed to arrive at this mode shape and you increase the load further, physically, what do you expect to happen? If it becomes 1.5 times that force, what do you expect to happen? So this bent thing will become more bent. Okay, as simple as that. Okay, whatever the deflection was, it is going to increase. Is it not? It is going to increase. Now, if you look at these kinds of, guys, settle down. Look at it. Now, if you just look at this formula, the kind of picture it tells us is that it is only at this discrete values you are going to have these buckled shapes, right? So P is equal to pi square EI by L square we have already seen. Then P is equal to 4 pi square by L square we are going to have another mode shape. Then 9 EI by L square another thing. And as if between 1 and 4 magically things will disappear. This is what the theory is telling us. Okay, between 4 and 9 magically things will become straight. There is no buckling. Okay, this is what it is telling us. Okay, so where do you think the discrepancy is? Is it that you are thinking wrong here, or is the maths wrong? No. You say one thing only. My question is, when I asked you that beyond that pi square EI by L square, if I increase the force, it becomes more bent. Okay, versus the kind of picture that thing is telling us that it is only at those discrete shapes you are going to have those things. Which one is the correct picture? First one is the correct picture, absolutely. Okay, it is actually the limitations of this theory that is giving us that kind of a discrete picture. All right, there is actually a limitation in this theory. So you actually have advanced theories where it doesn't predict it like this. Okay, so beyond the buckled shape, what happens, this theory is not able to tell us. It is only able to tell us what are the kinds of stable buckled shapes it is going to predict. Nothing more, nothing less. It is only those discrete values it is going to tell us. But this theory cannot tell us what happens in between. Okay, so yes. Second limit means this one. No, that is not the issue. That is not the issue. Okay. There is one issue which I can tell you directly is that you remember that EI d square y dx square, that itself is an approximation. We have not taken the full, non-linear version of the curvature into account. That is one issue. Okay, so whatever happens in the post buckled shape, that is not being able to capture. Okay, so don't worry about it. Okay, if you ever study advanced mechanics of solids or things like that, you'll be able to learn it. But for now, you know that there is a limitation in this theory, and the mental picture that you have, that is absolutely correct. Okay, however, let's say that the thing is standing straight, and somehow very magically and very mathematically precisely you are suppose able to trigger that 4 pi square EI by L square. Then what will happen? Then actually you are going to get the second mode shape. But in reality, the thing is, you never do it like that. You first apply a force and then you keep on increasing it. So always what will happen is that this Euler's first critical load, that is going to get triggered. And once that gets triggered, the rest of them actually don't matter that much. So in reality, this is the fundamental mode like in terms of actual engineering, that is the more important thing. Okay, those are there. Those are certainly there from a mathematical sense, but this is the one which is actually physically realized. So this is the one which is the most important one from a physical point of view. Okay, all right. So time to go on to other kinds of boundary conditions.
So,
Yes.
you say that the reason why this is failing is because, like you said, the EI, the level differential is that is we're not taking the full expression into account. So, from that, can we say that the Y value at the conclusion is very less, which is why we are not going for the terms into account.
Absolutely. So what Akshat is saying is that because we are limited to that small y thing, okay, small y, small curvature, all these things, it actually doesn't make sense for us to expect that this theory is going to work if we keep on increasing the deflection. The whole thing actually falls apart. Yes, right. Okay, so let us move on to another boundary condition. We'll consider a mechanical member which is fixed at one end and the other end is free. So if you rotate this picture 90 degrees, then it will just look like a cantilever. Okay. But unlike the usual cases of cantilever which we have come across till now, the tip load that we are going to give is not going to be a transverse load, rather it is going to be an axial load. Like this. And again, we are going to consider a deflected shape of this member also. So the deflected shape will be like this. And we'll say that whatever this deflection is, this is going to be delta. We do not know a priori what delta is. Please write this down, that delta is not known. Okay, so delta is not known a priori. All right, so just like before, we are going to take a cut section and we are going to investigate that cut section. Now we have to be a little bit careful in tracking the deflection now. Note that my coordinate axes are again set up like before. Downwards is x, this thing is y. Now if I look at this cut section, this much, how much is the deflection? Y, right? That deflection is y, and at the top the deflection is delta. Knowing these two pieces of information, can you tell me what is the moment arm of this force P if I take the moment about an axis which is passing through this end? The magnitude will be delta minus y of that moment arm. Okay, so we have to write this carefully. So the moment balance, for the moment balance equation, about an axis which is passing through this end, it will be m from this, and from here it will be what? Correct? Please convince yourself that this is correct or not. ठीक है? Okay? All right. This m I will replace by pi d square y dx square minus p minus y. This will be plus py, and I will have a P delta over here. Okay. And again, just like before, I'll divide throughout by EI. Right? Now the earlier form was d square y dx square plus k square y is equal to 0. That was a homogeneous equation. Okay. So we did not have to worry about any kind of particular integral or particular solution. But now this is no longer homogeneous. So this part is there, because of which we'll have to consider the particular integral or the particular solution. Okay. Now there are, in your first year, you have learned various methods of solving differential equations having particular integrals. And tell me some names. Huh? No, no. I'm asking about the particular integral. Finding out that method of undetermined coefficients. Yes. Huh? No? Acha, okay. Whatever. You learned something. You learned something. Let's put it like that. Okay, you learned something which you have forgotten, but if you revise, you will remember. Oh, all right. Now, there is another method. Okay. Method is that, okay, you put down your pen, okay, and you look at it. And you look at it hard. Okay, and you guess the solution. That has a name. It is called finding out the solution by the method of inspection. Okay, because everything has to be formalized. So you tell me this thing, if I did not tell you anything, okay, so consider for a moment that it is now JEE mains and you have to beat the rest of India. This is, I mean, life is hanging in the balance. You have to find a solution. You do not know any other method. You just have to match it. What will you do? What is the particular solution of this? Y is equal to? Y is equal to delta is a solution. Okay, y is equal to delta is a solution. Why? Because this delta does not depend on x. It does not depend on y. It is just a thing. Okay, so if you take y is equal to delta, this d square y dx square doesn't contribute, it gives a 0. So all that remains is this k square y. So this is k square delta. Left hand side is k square delta, right hand side is k square delta. So we are happy. Okay, so method of inspection is the best method when it works. Okay, so actually for most of the problems that we do in this chapter, you will see that the method of inspection actually works. Kind of. All right. So, and the good news is that if you can somehow find out a particular solution, you do not have to worry about anything else. That particular solution will help you out. Okay, it is a particular solution, right? There is no, I mean, doesn't matter how you got it. Okay, so a particular solution absolutely works. So all that you have to do is combine the complementary solution or the homogeneous part with the particular solution. Now what is the homogeneous part? D square y dx square plus k square y, that is equal to 0. What is the solution for that? Earlier we did that. Y is equal to a sin kx plus b cos kx. So you already have that, and you have the particular solution also, which is y is equal to delta. All right, that is the solution. So this was not the challenging part. Okay, challenging part will come now, because now we have to deal with these unknown things. What are the unknown things now? No, no, k is known. K is known in the sense that, I mean, if you say that you know p, then see, a is not known, b is not known, but delta is also not known. We have given a name to it, but it does not mean that we know it. Okay, we do not know it. So we have to do something about it also. All right. Now, you tell me what boundary conditions can I use? Like in a very practical way, you think about it. What are the boundary conditions I can actually use? Tell me. At x equal to L, at x equal to L, y equal to 0. At x equal to L, dy by dx is also dy dx is also 0 because slope is 0. Okay? I am not telling anything new. We have done this in the deflection chapter. So if you have a cantilever beam, at this end, you have the deflection 0 and the slope 0. That is all that I'm saying. Except now that you have it at this end, at x equal to L. Okay, please note that x equal to 0 is here. This is x equal to L. So at x equal to L, you have y equal to 0. At x equal to L, you have dy dx equal to 0. What else do you have? Very good. At x equal to 0, you have y equal to delta. That also is a condition. But we'll see how we use it. So one by one, we'll do it. Okay, at x equal to 0, y is equal to 0. Oh, sorry. At x equal to L, y equal to 0. So this gives us A sine KL plus B cos KL plus delta equal to 0. Right? Next, at x equal to L, dy dx is equal to 0. Now dy dx we have to do. There is no other way. Okay. So from there, you note that dy dx is ak. So let me write the dy dx first. Ak cos kx minus b k sin kx and d delta dx is 0. Okay. So at x equal to L, what we are going to have is ak cos kl minus b k sin kl, that is equal to 0. Right? Now, of course, we are going to use x equal to 0. At x equal to 0, y is equal to delta. But before that, just pause for a moment and let's say that I tell you that okay, for a moment don't worry about the delta. You find out the solutions for A and B. I mean in terms of the delta only. Can you do that? I hope you have understood my question. You try to find out the solutions for A and B in terms of delta. Can you do that? Say you have two linear simultaneous equations. This is one linear simultaneous, this one equation, this is another equation. So of course you will be able to do it, right? Huh? Yes, you will be able to do it. Okay, what will you do? Don't do anything. Don't do anything. There is a trap. There is a trap. Okay. So what will you do? So here you have, okay, this k goes away. What will you do? A cos kl is equal to b sin kl. And then what will you write? Maybe A is equal to B tan KL, right? Okay, A is equal to B tan KL. Now, A is equal to B tan KL. Now, what will you do? You will come here, okay, and then you will substitute A is equal to B tan KL. If you write B is equal to tan KL, then B tan KL will be this, with this, it will be B sin square KL divided by cos KL. Here is cos KL. Things are shaping up beautifully and it will make you very happy, right? What is going to happen? Let me tell you. Okay, so B sin square KL, this cos KL multiplied with this plus B cos square KL. Like this is beautiful. Okay, now the way that you are proceeding, nothing can be wrong. Like God wants it like this, right? So this will be B by cos KL, right? B by cos KL plus delta is equal to 0. B has come out. B is equal to minus delta cos KL. Without writing a single thing, we have done it orally. What could be better than this? B is equal to minus delta cos KL. And A is equal to B tan KL. From that also we are getting A. So A and B done. Okay. Now, you do it. Just do it in 2 lines. B is equal to minus delta cos kl. From that you write so I'm putting two hash marks here. Okay, there is a trap here. That's why I'm telling you. So this A is equal to B tan kl. From this, what you are getting, B is equal to minus delta cos kl, and A will be minus delta sin kl. Right? है ना? Okay. This is what you are getting. Now what will you do? At x equal to 0, what are you going to do? Y is equal to delta. Okay? So just do it. This is the thing, right? Please do it. Yes? So A is what? A is minus delta sine KL. And sine, this is 0. B is minus delta cos KL. Cos K0 is 1. Okay? Right? This delta has cancelled with that. So you are getting this. Delta is not 0. So you are getting what? Cos KL equal to 0. So life is good. Okay, where is the catch? Huh? Very good. Okay. What is your name, sir? Ved. Ved. Okay, Ved. So Ved is absolutely correct. So it seems all very nice and good, except that there is a fundamental problem. Fundamental problem is that here what we have done is we have divided throughout by cos scale. So the moment we do that, we are implicitly assuming that cos scale is not 0. So A is equal to B tan KL, so cos scale is not 0. But ultimately the condition that you are obtaining is that cos scale equal to 0. Okay. So it is self-defeating. So everything has gone wrong. Okay. Actually nothing has gone wrong. Okay. This is the correct condition. Except that we have to proceed in a slightly different way. Okay. Destination is the same. We'll get cos scale equal to 0. There's nothing wrong with it. In between we have to do it in a slightly different way. Okay. So what we'll do? We will say that we are not going to solve it. Rather, we'll put it in a matrix form. Okay. So matrix form means what? What are the things that we don't know? So A and B. Now, can I write like this? Sin KL, cos KL. Delta is also not known, so we'll put it like this, 1. This one is what? From this condition, what is it? Cos KL minus sin KL. Do you have any coefficient for delta? You don't have any coefficient for delta. So this is 0. What will be that equation? The last one, at x equal to 0, y equal to delta. So coefficient of A is 0. Coefficient of B is what? 1. Okay. So it will be 0, 1, and then 0. Okay. So this will be your entire system. On the right hand side, what will you have? In order to write this entire equation, what do you have? Right? This is the thing. I have not done any mathematical crime. I have just set it up like a matrix equation. Okay. Now you go back to the previous problem solution that we did, which came out very nicely. That b was 0 and a sine kl equal to 0. What was the condition that we imposed finally in order to arrive at sine kl equal to 0? What did we write? That little phrase that we wrote. For non-trivial solutions. For non-trivial solutions, we said that a cannot be 0, therefore sine kl equal to 0. Now let us come back to that phrase only. You see, this is a system of equations. And again, we want to have non-trivial solutions out of it. If we want non-trivial solutions out of it, what is the condition? The determinant has to be 0. Right? The determinant has to be 0. Now, if you use the determinant equal to 0, then what are you going to get? Just see. See, it doesn't matter which row is where. This row could have been upstairs also, okay, in the first row. So ultimately what you'll do is, you can expand in terms of this last row. Okay, you can expand in terms of this last row. What will happen? This 0 into this entire thing, this minus 1 into this diagonally opposite things, and then plus 0 into this. So ultimately what will happen is that, let me write it down. I'm just being a little bit lazy here. I've just written it like this, okay? I've not written the entire thing again. So determinant of whatever that matrix is, that is going to be equal to 0. So this is minus 1 into sine kl into 0 minus cos kl into 1. That is equal to 0. So I have expanded in terms of the last row. Okay. So what does this give us? Cos kl equal to 0. Okay. So we are again back at the same thing. Yes, Akshat, what are you worried about? Huh? You are thinking that the determinant is equal to 0 or not equal to 0? Huh? It is equal to 0. So for non-trivial solutions to exist, the determinant has to be equal to 0. Okay. All right. So cos kl equal to 0 is again what we arrive at. And please note that earlier also, when we were doing it in a very innocent fashion, then also we arrived at cos kl equal to 0. Okay. So there is nothing wrong with the ultimate solution. It's just that we have to be a little bit careful with the way that we proceed. Okay. Fine. You complete up to this, then I'm going to torture you a little bit more. Yes. We did not divide by sine kl. Acha, could we have divided by sine kl? Yes, we could have. Yes. I deliberately did not do it because it does not create a problem. Ha. Yes. So what he's suggesting is that, suppose instead of writing a is equal to b tan kl, suppose we wrote b is equal to a cot kl, then it does not give rise to any of these problems. But it also does not give me an opportunity to give you this funda. Okay, which is why I chose this wrong method deliberately. It's not wrong, but so all done till here, cos kl equal to 0. Let me finish it up. So if cos scale equal to 0, what does it imply? Cos scale equal to 0 will be true when? When kl is equal to odd multiples of pi by 2, pi by 2, odd multiples of pi by 2. So let us write it like this. Okay, twice n minus 1 pi by 2. The reason that I am choosing twice n minus 1 and not twice n plus 1 is that I want to start with n is equal to 1. If I write twice n plus 1, then I'll have to start with n equal to 0. So it's a little bit different from the previous case where we started with n equal to 1. Here also I want to start with n equal to 1. So twice n minus 1. Okay, all good. And again, like before, we are going to be interested only in the fundamental case, meaning where n is equal to 1. Okay, so for the fundamental case, this kl will be equal to pi by 2. By the way, that dangerous thing that we did, please put a skull or something around it. Okay, or at least put a cross around it. Don't do it like that. Please write this much down. Please write that down. So P is equal to pi square EI by twice L whole square. This is the fundamental case corresponding to n is equal to 1. All right. Now you tell me something. Earlier, we were obtaining for the pinned case, P is equal to pi square EI by L square. Now there is a reason why I have not written it like 4L square. Rather, I have written it like twice L whole square. The reason is that when we have this fixed free case, then it is as if the effective length is twice L. Okay, so this is something like the effective length. So every time we will pay homage to Euler, okay, for his formula pi square EI by L square, and we'll try to re-represent everything in terms of that famous Euler-Buckling formula. But of course, these new coefficients will keep on coming for the different cases. We will combine them and tell that that is the effective length. The twice L is the effective length. Now in Beer and Johnson, what they have shown very nicely is that you can almost imagine that this here is the pinned case. It is not. Okay. Imagine that this is the pin, and if you extend it, it is like this. And there is a pin at the other end. Okay. So overall, this becomes twice L. In that sense, that is twice L. Okay. But after you have done the maths, it is good to pull off these kinds of mental stunts. Don't pull off these mental stunts and bypass the maths. Okay. Okay. Next case. So this time we are going to consider a clamped at one end and pinned at the other end. Okay. Some of you may be slacking off a little bit in the sense that recording तो हो ही रहा है तो लिखना छोड़ देते हैं. Please don't do that. Okay, so keep on writing it. Later on, you do not have to, will not have to rewatch it. So from the 2021, I have actually a playlist of mechanics of solids, and you will see that in the very first lecture there is one comment from one of your seniors. Not going to class only to look at these lectures again. Okay, that is the most philosophical comment you will see. Okay, so please take some heat from your seniors' follies. So this is our situation. So at the bottom we have this clamped or fixed end, and at the top it is a pinned. And again, this is our x, this is our y. Now as before, we are going to consider the deflected shape. Okay, but we have to be a little bit careful in how we represent the deflected shape. You see, here the rotation is not prevented. Okay, so it will be something like this. Okay, drawing the diagram correctly doesn't help you to do the maths, but it at least you will be able to appreciate these boundary conditions. Okay, so what is the procedure? You take a cut section, write the moment balance, and proceed from there. So again, we'll do that. Right? See, in every problem there is a little bit of a trap and little bit of a twist, okay, which makes life interesting. Okay, so here also you will see that it's not going to be boring. Now you see, from here there is nothing else. See, it is exactly like the first thing. So what? If you take the moment balance about an axis which is passing through this bottom end, then it is going to be m is equal to minus py. As simple as that. Which means that I can actually write it in exactly the same fashion as the first case. Right? So far nothing bad. Okay, things are same. What could be more beautiful? Okay, equation is same. Now you see, after we have, this is the equation. There is nothing wrong with this equation. What is the solution of this equation? Y is equal to a sin kx plus b cos kx. Nice. Nothing wrong with it. What about the boundary conditions? Because I have to address the a and b. So you look at this. At x equal to 0, y is equal to 0. At x equal to L, y is equal to 0. Now if you do all, wait, it is a second order differential equation. You need only two boundary conditions. I have already given the two boundary conditions. So where will the change occur? You realize what has happened. In the first case, we had this same equation. The condition was completely different. It was a pinned case. There also, at x equal to 0 and x equal to L, we had y equal to 0. Now also, at x equal to 0 and x equal to L, I have y equal to 0. There is nothing wrong with it. Now if I use those two conditions, then what will I arrive at? The same kind of thing. Does that make sense? What am I missing?
It is more constrained.
How it is more constrained. It is more constrained. That much is true. Okay. So what can we do?
X equal to
Now, some of you can argue that okay, we'll not use that at x equal to 0, y equal to 0. We will use at at x equal to l, y equal to 0. We'll use at x equal to l, dy dx equal to 0, and maybe something else will happen. But this is where I'm guiding you. Okay. Now, in which case will you know that things are going to work out, and in which case will you know that things are not going to work out? Suppose it could be a situation that here there is a spring and there is maybe another case which is completely free and the load is somewhere below. So you can have different conditions. What are you going to do? So see, the shortcoming of this second order differential equation method is that it does not encapsulate the entire physics or the entire mechanics. Okay, why it does not encapsulate the entire mechanics? Because it is a second order differential equation. You are not able to provide or you're not able to specify all the boundary conditions that are actually there. Okay, so would it not have been very nice if you could have very explicitly given both the boundary conditions that you know here and both the boundary conditions that you know here? What is the second boundary condition that you know here at the pinned end? What is 0? Moment is also 0. But now, because you are dealing with the second order differential equation, you do not have the flexibility or freedom to apply that condition, because m equal to 0 at that end is there, but you cannot use it for a second order differential equation. Okay, so what is the way out? Remember, in the deflection chapter we had looked at a fourth order differential equation version, right? So remember that d4v dx4 by differentiating twice is the exact same thing that we are going to do now. Okay, so from this second order differential equation we are going to arrive at a fourth order differential equation by differentiating it twice, and that fourth order equation will admit more number of boundary conditions where we can peacefully apply all the things which are there in the actual mechanics. Okay, so let's do that. So I have not done anything fancy. I just differentiated twice. Okay, and I have arrived at this fourth order version. In the deflection chapter also I had done exactly the same thing. You can look back at your notes and see. Now, some of you who are more mathematically inclined may think that what is this kind of hodgepodge method? I had an equation, nice. Now I have differentiated it twice, and unnecessarily I have arrived at this fourth order differential equation just because I wanted to use more boundary conditions. There should be something more fundamental, a more fundamental way of arriving at this fourth order differential equation. There is. Okay, there is very much. So you can think in terms of moments and shear forces and proceed from there, or if you want to be very precise mathematically or very like formal, then there is a method called the calculus of variations. Okay, and through that you can find differential equations and boundary conditions at the same time for beams, for plates, for shells, all the things. Okay, of course that is beyond the scope of this second year course, so we will not go into all that, but let me just tell you that even if you do the calculus of variations method, ultimately the fourth order differential equation that you obtain is this only. It is exactly this. Okay, but the good thing in that calculus of variations method is that simultaneously you also obtain all the boundary conditions. Okay, you do not have to go searching for the boundary conditions by looking at this situation whether it is like this or like that. Okay, naturally it follows. Okay, so it makes sense to study the advanced mechanics of solids also. Anyway, we'll proceed from here. So what are so again we'll assume the solution form. And if you do that, you end up with this thing. Further on, what are you going to get? So what are the roots of this algebraic equation? M square into m square plus k square. Yes? M is equal to 0, 0, 0. Right. So 0 is a repeated root. We have to take care of that. 0, 0 and then ik and minus k, minus ik. Okay. It is very important for us to note that there is indeed a repeated root in the form of 0, because it makes a world of difference to the actual solution form that we are going to write. Right. Okay. So what is the solution form? So y is equal to c1 e to the power ikx plus c2 e to the power minus ikx plus, what should I write for the 0 and 0? Right. So I'll write it like this, cx plus d. Okay, cx plus d. Those of you who are a little bit crestfallen, please go back to your first year engineering maths notes and take a look. Now this thing is exactly the same form as earlier. Okay, so if I expand it by the De Moivre's theorem, I'll finally end up with the form that's it. Okay, so y is equal to a sin kx plus b cos kx plus cx plus d. The good news is that now we have 4 unknown constants and we can very nicely specify 4 boundary conditions. So now you tell me what are the 4 boundary conditions. At x equal to 0, there is no doubt that y is equal to 0. And that gives us what? B plus D equal to 0. Okay. Next. At x equal to 0, I have m is equal to 0, which implies that d square y dx square is equal to 0. Actually, to be formally correct, I should have written this as ei d square y dx square equal to 0, but since there is a 0 on the, let me write it. Since there is a 0 on the right hand side, this ei might as well cancel. Okay. So now I have to write this dy dx. This will be ak cos kx minus b k sin kx plus c, and then the d square y dx square will be a k square with a minus sin kx minus b k square cos kx. That's it. Okay, so for that m is equal to 0 condition, I'll have to substitute x equal to 0. So this thing applied now right? B is equal to 0. Now if B is equal to 0, you see B plus D is equal to 0. From this I can conclude that D is equal to 0. Now you may be already thinking that in the previous case I proceeded by the determinant equal to 0 method, so probably it will be safer to proceed by that method. You are absolutely right. It is safer to proceed by that method, but as long as you are not dividing by anything or multiplying by anything, you are good. Plus minus can be done. Okay, there is nothing wrong with it. So B is equal to 0 does indeed imply that D is equal to 0. But let's not utilize it right away. Next, at x equal to L, y is equal to 0. Okay, at x equal to L, y is equal to 0. So what does that tell us? B is equal to 0, D is equal to 0. Next, at x equal to L, dy dx equal to 0. So I already have my expression for dy dx. AK cos kl minus bk sin kl plus c equal to 0. This thing is 0. So this is AK cos kl plus c equal to 0. Now, one thing that you can do rather safely is to consider just these two as your equations. Okay, as just these two as your equations, and then you can put them in a matrix form. Okay, that you can do. So so sin kl plus L, and then from this one we'll have k cos kl, and then plus 1. This thing is equal to again we want non-trivial solutions. Okay, so for non-trivial solutions, what is the determinant? Sin kl minus kl cos kl equal to 0. This is the condition that we have. Okay, so sin kl minus kl cos kl equal to 0. Now there are no other steps left. Okay, so you can take a deep plunge into the dangers and you can divide by cos kl. Okay. Now, what kind of an equation is this? It's a transcendental equation. You will not be able to find analytical solutions this unless you take some kind of like asymptotics or do something like that, or you can just do it numerically. Okay, you can do numerically. So I suggest, because we have run out of time, uh, you try to find out the solution of this numerically. Okay, you can ask ChatGPT or Claude. There is one thing, but try to find out from your calculator if you can find it out. Okay, I think some of you have class after this, and I also have to pack up. So maybe do it in your room, and we'll continue with this discussion tomorrow. All right, thank you.